All right, everyone. Thanks for having me. Fun fact, I think I presented either the first or second TT Lab meeting, these weekly seminars, and that was over a year ago. So it's nice to see it still going on. So today I'm presenting on perceptually motivated video restoration. I guess most of you all should know me. My name is Darren Ramsook. I'm a PhD student at Trinity College, Dublin. So I started at TCD in September 2020 under the SIG Media Group. The official PhD title is Video Coding Artifact Suppression Using Perceptual Criteria. And my work is supervised by Dr. Anil Kokram. I'm funded by a mixture of funding from DREAL, which is part of Science Foundation Ireland, and Google. I completed my master's in data science at UE, and also completed my bachelor's in electrical and computer engineering at UE as well. So besides work, I actually appreciate music a lot. I put that in green there, just to emphasize that point. You can find out more about me from this website. And also feel free to contact me at any of these emails. Okay, so we're just going to talk a little bit about the background before we actually start the presentation itself, just to make sure we kind of have an idea of what's happening and just to help with following along. So we're going to talk about how images are stored in computing systems. So you could store a single color shaded image, for example, a grayscale image, by using a 2D matrix. So that's this matrix on the left here. You could also store colored images by using a stack of RGB matrices. So that's this 3D representation here. If you display this stack of red, green, and blue matrices upon each other, you'll get some color value that will correspond to an image. And the values of these matrices differ depending on the objects on screen or the color of the objects on screen, etc. So what is video then? So video is just a stack of these 3D matrices. So you take one frame, which is an RGB frame, and you just have a stack of them. So that's what this thing is here. This is a 3-frame sequence. So at first we have 2-dimensional, just height and width. We added 3rd dimension for color, and now we added a 4th dimension for time. So yeah, things kind of get a little hectic when you start going in these areas and even in VR areas and stuff like that. Okay, so this is just a representation of a 2D image, just one image, on the RGB matrices that when you put them together, you get this image. So you stack this image on top of this image, on top of this image, and you display them and you get this colored image. So you see there's a lot of red happening in this image here on the left. And you could see that in the red channel, this first image here, it's mostly white, which means high intensity for red. And you see his eyes are blue. So you look at the blue representation here and the light values, which means high intensity for blue. So this is a fun way to represent images. However, represented using RGB, red, green, and blue, is not always good when you're talking about algorithms and implementing algorithms. That's because RGB is strongly correlated. We want to use a representation that is not correlated or uncorrelated. So YUV, which is luma, chroma blue, chroma red, that's what YU and V stands for. Kind of counterintuitive, I know. Y is luma, U is chroma blue, and V is chroma red. But this is a non-correlated representation. So you could transfer from RGB to YUV and back to and fro without you losing any information. And the good thing about YUV is that it's non-correlated. So developing algorithms and different mathematical structures is a bit easier. And a nice thing to know about YUV is that the Y channel corresponds to most of the perceptual information in the image. I believe I read somewhere it's between 90 to 95%. So if you make a change in the Y channel, you'd see it. However, if you make changes in the U and V channel, it's not really noticeable. And this is used in representing internal matrices in MP4 video, etc. For example, for every 4 Y pixels, there'll only be 1 U pixel and 1 V pixel. So it's sort of a subsample that's occurring here. And to me, if you use this representation with of 420, that's the term they use, 4 luma to 1 blue and 1 red, you really don't see difference perceptually. I don't see the difference really. Okay, so now the actual introduction to the presentation. So video accounts for about 70% of all network traffic. This prediction was done in 2019. So, I mean, this measurement. So I believe since the pandemic hit and Netflix subscribers and other streaming services has gone up, I believe this percentage to be a lower estimate by now. And the current predictions are on track for 80% by 2022. So if you think about it, all the network traffic that's happening in video corresponds to the biggest chunk of that. And that's because video, the data itself, the representation of itself, it takes a lot of bits to represent an image, and more or less a sequence of images would be even more difficult to represent. So compression is the main reason video has not overwhelmed current architecture. So for example, if you're streaming a 4K ultra high definition clip at 24 frames per second, you need a bandwidth of 4,777 megabits per second. This is an uncompressed clip. So if you're just using it, the raw clip, this is the bandwidth you need. If you want to store a 30-second clip of this 4K at 24 frames per second, you need just shy of 20 gigabytes, which is kind of crazy when you think about it. But we know today that on Netflix, you could stream 4K content pretty easily. So whenever you compress, you introduce artifacts. And this is lossy compression, which is thoroughly used. So some artifacts you introduce are noise, banding, and blocking. So here's some small examples of artifacts being introduced. On the top left here, we have banding. This is something that once you see here, and now that you go to look at a movie on Netflix and you see it in the back of your mind, you'd say, oh, there's banding happening in this shot. So banding typically occurs because of the quantization levels of the color bits. What that means is that you get this kind of these concentric rings over gentle color gradients. So on the left is the original, on the right is what you get after compression. You also get blocking. So on the left you have an original, and right we have some blocky artifact. Also have some noise added, but no, typically you don't have this amount of noise added, but this is just for demonstration purposes. This is additive white Gaussian noise on the right here, and the original on the left. Okay, so now we're going to talk about quality measurement of images and video. So right now, PSNR, or peak signal to noise ratio, is the current go-to, and that's used to assess the majority of algorithms. And this is based off the mean squared error function. Why MSE? Well, MSE is just very simple to deploy and easily understood. I think this is the de facto standard for training regression neural networks. Yeah, so in this case here, if we have some restored image x hat and the original image x, we could calculate the mean squared error by just taking difference and squaring them. And then we could find the PSNR through this formula here. So what does this say? This says that the lower the MSE, the higher the PSNR. The lower the error in the restored image, the better PSNR you get. So PSNR is a good measurement, but however, it's not an accurate representation of the human visual system. The human visual system is just a fancy name for your eyes and your brain and how those two things interact with each other to interpret images and video. And we know that the HVS depends on local correlated features such as luminance and structure. So from off the bat, you could see that PSNR is a good metric, but it's not really a good representation of what we see. It's good, it's easy to use in most of the software packages we have out here. I think MSE is there by default. So there are other metrics coined by this nice long term here, complex perceptual visual quality metrics, or PVQMs. These better represent the effects of perceptual characteristics of visual media on the human visual system. So what does it say is that these metrics better correlate to the perceptual behavior of humans. The VMAF function, the Video Multi-Method Assessment Fusion function, is one of these perceptual metrics. VMAF is a very popular open source model. It's spearheaded by Netflix. Netflix actually uses this in their internal compression algorithms to create good representations for distribution. However, VMAF is non-differentiable. So you can't use that in deep learning scenarios. And we'll see how we're going to use that later on. So these complex PVQMs, you typically use them in assessing performance in post-hoc scenarios. So for example, you have a new compression algorithm or a new restoration algorithm. It uses a PVQM, such as VMAF, to see how well this algorithm is performing. What's the quality like at the output of this algorithm when measured to the input? And it's not actively used in the loss function. So for example, MSE is actively used in the loss function. You use that a lot in deep learning networks for images and video. These PVQMs like VMAF, they are not used because, first of all, it's non-differentiable. So for deep neural networks, you need something that's differentiable to propagate the error through the network. So this is a nice representation of what I talked about just now. On the top left here, you'd see a nice image. This is the original clean image with a mean squared error of 0. So this is the original image here on the top left. So all other representations are noisy corruption of this image. So off the top of your head, what would you say is the closest visual match to this top left image from selecting all of the images? I would say one of these at the bottom row here. Probably this one, even this one. However, if you look at the mean squared error scores, which is the first score underneath all of these images, we see that the mean squared error for these representations are quite high. So this one that I chose is 871. So if we look at which score has the lowest, we see that this one is actually lowest. This is 306. However, we can see that the colors don't really match up to the original. Look at this one. This one is 309. It's an MSE of 309. However, this is a very noisy image. So according to mean squared error, or PSNR, this image is a better representation of the original than this image, which is not the case visually. Similarly, this one, this blurry image, has a mean squared error of 308. It's not a good representation of the original. I'd still choose any from this bottom row here. So what we did is we proposed a training method For deep neural networks in restoration scenarios, we train those networks using complex non-differentiable PVQMs, such as VMAF. And we propose this method for use in video. So we took existing denoiser networks and we retrained those networks using our proposed method and also we extended previous work that looked at this this method of training for still images. So previous work done that looked at using perceptual optimized model for still images extended for video by including temporal components. So previous work looked at using these non-differentiable PVQMs such as VMAF in restoration scenarios for still images. We can't use still image models for video because video has temporal information passing from one frame to another. And we know that there's extensive work in restoration networks. So we looked at successful existing networks in a denoising scenario, and we implemented our training method in this denoising scenario. We'll talk more about this in the coming slides. So the general mathematical framework, I won't spend too much time on the formulas, but I'll probably just give a quick run through. So given a video sequence IT, we want to create a corrupted sequence by introducing additive white Gaussian noise omega t. So we could do that simply by taking IT and adding some white Gaussian noise omega t to get I tilde t. So now we want to denoise this video. We could use a deep neural network, and that deep neural network would be labeled D, some network D, parameterized by theta d. It takes as input I tilde t, which is the noisy frames, and it tries to produce some output I hat t. This restored output is what you're trying to get IT, and that's what this loss function here represents. So to train this deep neural network, typically you'd use something like the mean squared error loss, which is the difference between the predicted output I hat t and the original reference input IT. So off the bat, you see that in the first few slides, I talked about how mean squared error is not really a good way to represent video, to represent perceptual metrics for video and images. But here we are using MSC to train our deep neural network. So here again, we have some general architecture for a spatio-temporal denoiser network. So in this architecture, we have the inputs on the left and the output on the right. In this architecture, we take a series of 3 patches over a 3-frame sequence. These are noisy, corrupted patches. We denoise these patches spatially, independent of each other. And then we merge those patches together to the input of a temporal denoiser to finally get some output patch that is centered or that is based on center patch T. So what this network does is it takes in 3 patches over a 3-frame sequence and gives you 1 patch. So if you have 5 frames, you'd get 3 frames at the output. One benefit of using this type of neural network over traditional neural networks is that if we go back to the previous frame and we want to restore some arbitrary length t, typically when you're talking about arbitrary lengths, you think like recurrent neural networks, so LSTMs. However, they suffer from memory loss, and in terms of video and images, these things could get pretty complex. So we limit the input and output sizes of the architecture for a better sense of stability across the network. So now we're going to talk about the spatial denoiser and the temporal denoiser. And we're going to start to discuss how we're going to train the spatial denoiser using not only MSE, but also using VMAF. And we're going to do the same for the temporal denoiser. Okay, so for this, first of all, the spatial denoiser. So the spatial denoiser, DS, which is a neural network, takes a single patch as input, I tilde, and restores and generates a restored patch I hat. So what this says is that DS takes in I tilde and you get this restored patch at the output. So this spatial denoiser can be trained using a perceptual criteria through this proposed composite loss function, LC. So this looks like a bit much, but the point I want to try to hammer home here is that it's made up of two loss values, this lambda loss here and this LP loss here. So first of all, this LP loss that I'm hovering over right now, that's a traditional loss. This is a mean squared error loss. And the lambda loss is a perceptual loss. We'll go into detail on how we're going to generate this perceptual value here in a second. But all this loss function says is that you're taking some weighted value, some weighted combination of your traditional MSE loss and some new perceptual loss, and you're going to use that in the loss function to update the denoiser network rather than using traditional mean squared error. Okay, so this lambda loss is the perceptual criteria, is the difference between the perceptual score and the upper limit of that score. So in our case, we're using VMAF. The thing about VMAF is that it ranges from 0 to 100. So 100 is the highest possible value for VMAF. So this perceptual score here is you're going to look at the VMAF of your restored output I hat compared to the original input I, and that's what VI represents. And you want to minimize that distance from VI to the upper limit. So in essence, what you're trying to do here is you're trying to close the gap between what the quality of your restored output is and the maximum quality that you could obtain with respect to VMAF. And we're not only using that, but we're using some weighted factor of the traditional mean squared error as well. But before I moved on, I know I said that VMAF is non-differentiable, which means you can't use that in a neural network. So what was the proposition? It's that we use a proxy neural network to estimate VMAF. So the proxy image quality assessment network, ProxIQA, is a differentiable estimate of VMAF. So this ProxIQA network denoted by DI takes in the restored patch and original patch and sort of gives you an estimate of the VMAF score. And this thing here is differentiable. And the ProxIQA network is trained using the difference between the predicted still image VMAF score, which is which is DI, and the actual score M. If you don't follow along this, it's fine. There'll be a nice diagram at the end. Hopefully, it'll be clear then. So again, the same process is happening with the temporal denoiser. This time, instead of taking in one frame, we take a series of 3 frames. We output 1 frame centered around time t. Again, the loss function looks eerily similar to the last loss function. It's because it is. However, instead of 1 frame, we have a sequence of frames this time. So again, we look at the some perceptual loss of the restored output and also some traditional loss, and we combine them using some weighting factor. And again, this lambda term here, this perceptual loss term here, is the difference between the upper limit of VMAF and the predicted VMAF score. And for the temporal denoiser, we have a proxy network that estimates temporal VMAF. So temporal VMAF is different to spatial VMAF. They use different characteristics in defining the final score. So we use a ProxVQA network, proxy video quality assessment network, as a differentiable estimate of a complex non-differentiable VMAF. So this ProxVQA is trained between the difference between the predictive VMAF score and the actual VMAF score. It seems kind of complex, but hopefully this diagram would help sort out any misconceptions. So this is just for the spatial denoiser. So let's just think about the spatial denoiser alone. All we want to do is put in one corrupted patch and get one restored patch. So that's what this corrupted patch is here, Italy. We put that through spatial denoiser network and we get a restored patch. This restored patch is then passed through to ProxIQA, and the reference patch is also passed into ProxIQA. At this point, ProxIQA's weights are frozen. So this neural network's weights are frozen. So you take the output, pass it through ProxIQA with the reference patch, and you get some estimate of VMAF. You take that estimate and you use it in the composite loss function. So that's what this LC is here. You calculate that loss and you use that loss to update the spatial denoiser network. After that's done, you unfreeze this network, the ProxIQA network. You look at the output again, but this time you're gonna also calculate the actual VMAF score. And this actual VMAF score takes the same restored output as well as a reference patch, and you're going to calculate the loss for ProxIQA. You're going to use this loss to update the ProxIQA weights. And a nice way of thinking about this is sort of a generative adversarial network. But instead of 0 and 1, which is what the discriminator would do in a GAN, you have sort of a range of 0 and 100 within the ProxIQA network. So what this does, it takes the restored output, calculates the VMAF score, an estimated VMAF score, tries to minimize that score with reference to the upper limit to that score. So the upper limit of VMAF is 100, and you use that in your composite loss function to update the spatial denoiser network. And then you use the output from the actual VMAF model as well as your proxy model to update your ProxIQA network. And that happens in one step. So similarly for the temporal denoiser, it's a bit more tricky to explain, but it's the same thing that's happening here, but just with a sequence of frames. So you have a sequence of corrupted patches. Each group of 3 patches goes into the temporal denoiser network, generates one output patch centered around the center time index. You take those output patches, you freeze the ProxVQA weights, pass it through ProxVQA, get some predicted VMAF score, and you use that in your composite loss function for the temporal denoiser. And once you do that and you update those weights, you calculate the actual VMAF score across this series of frames with respect to the restored output. And you use that to generate a loss that's used to update the ProxVQA weights. So in general, for both the spatial and temporal denoiser, this is the routine that you do. So first of all, you train the denoiser network. So to do that, you first of all freeze the proxy network. So you freeze this thing here. You pass corrupted patches through to the denoiser network. And then you take the output of the denoiser network and you pass it through the proxy network. You use the predicted VMAF score from the proxy network and the MSE, which is a traditional loss between the reference and restored patches to generate some new composite loss. You use this loss to update the denoiser network. Once you do that, you need to keep the proxy network in check as well, similar to a GAN. So you unfreeze the proxy network, you pass the output of the denoiser network through the proxy network, and you calculate the loss between your predicted VMAF proxy score and the actual VMAF score, and you update this proxy network. Okay, so now we're going to talk a little bit about the actual networks used for the denoisers. So for the spatial denoiser, we used existing networks. So this model was proposed by Tassano et al. From DVDNet. This is the spatial denoiser alone. So you just put in one patch and you get as an output one patch. So you see you put in a patch of size 50 by 50 by 1. This is then split up and stacked to get 25 by 25 by 4. You concatenate this with a noise map. So what a noise map is, it's a matrix where each location corresponds to the standard deviation of the noise in the corrupted patch. You take that data, pass it through standard CNN ReLU batch norm blocks with a large internal representation, and then the final layer, you have a 25 by 25 by 4. You reconstruct to the original dimensions. You have a residual connection here, which means that in reality, this patch here is a prediction of the noise. You subtract that noise from the original corrupted patch, and hopefully you get some restored output patch that is close to the original. For the proxy network, the ProxIQA network, which is the differentiable VMAF, or the estimator VMAF, we take in the restored patch as well as the reference patch. These patches are processed independently of each other using the same weights. So you take the restored patch, you pass it through this network here, and also the reference patch, and the resulting representations are then concatenated with each other. And then this concatenated representation is processed together as one. And then finally put some dense layers, and you finally get your predicted VMAF score. And you also have some residual connections along the way to help with any gradient issues. And for the temporal denoiser, we have 3 patches as input, 1 patch as output. The same it's very similar architecture to the spatial denoiser, except that the inputs, you have a sequence of 3 patches now. So a large internal representation of the CNNs, and you merge everything to get some predicted noise here, and then have a residual connection to the center frame, to the center patch, and you get some restored output patch. So this architecture isn't new. This is done by this was originally proposed by Tassano et al. As well. This, on the other hand, is the architecture for the proxy VQA, which is the temporal version of VMAF, or the estimated temporal version of VMAF. So we have the corrupted, well, the output patches here, the output restored, as well as the reference patches. These are processed individually, spatially, and then concatenated with each other, and then processed again to form some temporal characteristics. And this is done for both this restored branch and also reference branch. So what this network does really is that you take one patch, you extract some spatial features, you take another patch, do the same thing, and another patch, do the same thing, and then you merge those features together into one big block. You take that block and you process them together as one to extract any temporal characteristics. And you do this for both restored and reference. You take the output, you concatenate together, and then you further process, but this time as one block, and you get some predicted VMAF score. And turns out that this is a very good way of doing video tasks using deep neural networks. It turns out that like LSTMs and RNNs kind of suffer from memory loss, and especially for complex data like video. But if you limit over some certain window and you process things spatially first, extract spatial features, and then temporally to extract temporal features, it's sort of you guiding the network along, actually. Yeah. So to train these networks, we use the YouTube UGC 720p collection. And we use clips from the categories music, video, and vlogs due to their low levels of perceptual noise. We added additive white Gaussian noise to the Luma channel with a mean of 0 and a standard deviation set between 0 and 15. And then from this collection of clips, we selected patches of size 50 by 50 over the 3-frame sequences. And in the final data set, we obtained 88,935 examples for the spatial network and 55,608 examples for the temporal network. So within the context of the experiments carried out, we trained 3 models. The first 2 models use variations of the perceptual criteria. So the first perceptual model, we trained the denoiser networks using the composite loss function. That composite loss function is the loss function that uses perceptual criteria as well as traditional criteria. We also trained a fine-tuned model where we trained the denoiser networks using traditional MSE loss for 50 epochs, and then use the perceptual loss for the remaining 5 epochs. This was done because MSE, while it doesn't represent the HVS very good, the human visual system, it is easily convergible. So what this fine-tuned model does is it exploits the ease of convergibility of MSE, and then further tacks on any perceptual gains that to be had. And finally, a traditional model was also trained using the MSE loss function, which is a traditional loss function for all 55 epochs. So we use the deep flow network for motion estimation and compensation. That's used between the bridge between the spatial denoiser and temporal denoiser. It's not really important. You can use any motion estimation and compensation algorithm here. We also use the Adam optimizer for gradient optimization. And the alpha values, which is a trade-off between the perceptual loss and the traditional loss, we set those values to 1.5 e to the minus 3. And this was done because in previous work using a similar training scenario, but only for still images, this was the value used. So some initial results here, we could see that the fine-tuned model, which is the model that trained on MSE first and then perceptual afterwards, recorded the highest average VMAF on the test set, while the traditional model had the highest average PSNR. The perceptual model yielded the lowest PSNR and VMAF. However, the output has visibly less noise. So this is some very interesting results we got here. So what this says is that the traditional model, which you use the traditional mean squared error loss function, you'd get the best PSNR, and that's expected because MSE and PSNR are directly related. However, you don't get the best VMAF. If you use the fine-tuned model, you actually get increased VMAF, but worse PSNR. And if you use these straight perceptual for all 50 perceptual loss function for all 55 epochs, you don't get the highest PSNR or VMAF, but the output has visibly less noise on a whole. So we have an example of that here. So this is a patch from a video. On the left, we have the original patch. Right next to that, we have the corrupted patch. And then 3, 4, and 5 are outputs from the different models. This one here is the traditional trained model, which uses the MSC loss function for 55 epochs. Diagram 4 is the output from the fine-tuned model, which uses MSC for 50 epochs, and then the perceptual loss for the further 5. And finally, in the end here, we have the output from the perceptual model. So I'll probably leave it up to you to decide which of these three looks the closest to the figure I. Yeah. Similarly, we have another zoom patch here. And this is traditional, this is fine-tuned, and this is purely perceptional. So yeah, I'll leave that up to you again to decide which one looks as closest to figure I. So in conclusion, we could say for certainty that traditional metrics such as MSC do not completely represent the nuances of the human visual system. In our work, we examined the use of spatial and temporal proxy networks that represent a differentiable estimate of VMAF as part of a composite loss function in a denoising scenario. We propose an extension of previous work that proposed still image perceptually motivated restoration. We use the YouTube UGC 720p collection to generate training and testing examples. And our results show that there's a potential increase to be made when using the perceptual loss, function for video. And statistically, you could get the best increase by using this as a fine-tuning steps, which benefits from the ease of convergence of MSC, and then tacks on any perceptual gains afterwards. We plan on using this perceptually optimized approach in deblocking. This should be interesting because VMAF was originally constructed using deblocking and artifacts directly related to compression in mind. So it'll be interesting to see the results from that experiment. And the work presented here is just a brief touch on these two papers. The first being a differentiable estimator of VMAF for video. This paper, we just spoke about the proxy networks and how well they perform. It turns out they perform quite well in predicting VMAF. And the other paper, a differentiable VMAF proxy as loss function for video noise reduction, we actually use the differentiable estimate of VMAF for video in a restoration scenario as part of a loss function. So in these papers, we go in much more in depth than what was presented here today. These are some references, and that's the end of my slideshow. So if there's any questions, or if I bored you all to death, you could let me know.
No, Darren, very interesting stuff. You know, kind of beyond my area of expertise, but couple questions. So, yeah. So basically, the idea is to use a linear combination of MSC and differentiable approximation of VMAF, right?
Yeah.
As the loss function.
Yeah.
The first thing is I forget how you define the combination, but you use a very small value of alpha, right? Which means the heavier component was which one?
MSC.
Okay, so you basically use a smidgen of the
Yeah.
VMAF stuff.
Yeah. Yeah.
And is that because of convergence issues or?
Yeah. So yeah, that's exactly why. So if you increase that alpha value, it's very difficult to converge. So the best approach is to use MSE as sort of a guiding point. And once you reach some steady state value, then the VMAF or the perceptual convergence, I don't know, trajectories of that loss would come into play and provide some extra perceptual gain.
Okay, so the VMAF is highly discontinuous then. It's
yeah.
The other so VMAF is fixed, right? It's a fixed mapping.
Yeah, so it's this big model done by Netflix using loads. It's a regression model actually. It's based on SVM.
Oh, and so is there any way to design that function more differentiable than they have it right now? Maybe even with a loss of
yeah. So that's a big question. And it's probably you getting the original data and using that to train a neural network could be one such approach, but something to note is that this architecture presented here, while I was saying VMAF, you could use any complex perceptual metric in place of VMAF. So there are a slew of non-differentiable complex metrics that you could swap out in VMAF. So once they have an upper limit or some fixed high endpoint, you could use that in this training architecture.
Okay, I mean, I guess this would be impossible to do, but there are subgradient methods as well for these things. But I guess in this case, it would be difficult to implement that. I don't know. I don't have a good feeling for subgradient. Okay, but thanks. Very interesting. Interesting stuff. No more questions for me.
All right.
Hi, Darren. Really nice presentation.
Hi,
by chance, have you essentially what you're doing is using surrogate optimization in place of the VMAF. By chance, have you all aside from neural networks, have you all looked at other surrogate models? And well, it's just two parts of question related to that. The other question is, have you considered looking at meta-heuristics like genetic algorithms or particles optimization, or probably mimetic algorithms that allow you to sort of use how to put it, that would allow you to sort of use like a gradient-based local search with respect to the MSE, but maybe use like the VMAF on the offset, anything like that?
Oh no, we didn't. I've never done any experiments in using that, but that seems pretty interesting actually. That seems like something I should probably write down, which I should do right now. Well, one way to easily wrap your head around everything, this is more of a statement, is that if you're familiar with GANs, so generative adversarial networks, and how you train a GAN by training in one step, you'd freeze the discriminator, train the original network, and then unfreeze the discriminator and train that network. It's sort of it's the same thing that's happening here. But instead of the GAN being 0, 1, it's more of it being the difference between the upper limits of the perceptual score and what the estimated score is. Should stop my screen. Yeah. Okay, any more questions?
Yeah, hi Darren.
Hey.
Interesting stuff. So just trying to wrap my head around what's going on. So
yeah,
let's see if I understand this correctly. So the VMAP stuff is it's not differentiable, so you're coming up with an approximate, right?
Yeah.
So any analysis of that approximation to say that it's good? Because I mean, since it's not differentiable, how close
Yeah.
to that is it possible? Like, for example, if you take the formulation for the VMAP, could you then just relax some constraints to get something that is differentiable, and then you could say, well, okay, it's just this much away from that, so therefore it should be close, right? It should be some sort of bound. So you get us some, like, any thoughts on that?
Yeah. So the first paper we actually did, which was, I should send that in chat, but and that paper we delved into how good this approximation of VMAF works, without any restoration in mind or anything like that. We just want to see how good it works, and it turns out it actually works pretty well. We got mean square error of 4.22, which means that the scores weren't deviating by much. So probably, yeah, I'll actually send you, I think I should send you that paper, but yeah, so in terms of the actual estimate, the estimate works well. There's some areas where the estimate doesn't work that well, however, and that tends to be where the VMAP scores are between 80 to 100-ish and 0 to 20-ish, which are like very good or very bad scores. But yeah.
Okay, cool. I'll message him email.
Yeah.
I mean, my background is in image processing and stuff, so it's really interesting.
Okay.
To see that I find it really interesting that you're using a non-differentiable something for.
Yeah. So
the whole math about it is it works because it's differentiable, right?
Yeah. So like VMAF, you use that after you create your model to measure your model. And say, so this time we kind of like switch it around using VMAF to train the model.
I still feel like if you could come up with some sort of differentiable function that would bound it, I think that would be like a much stronger position.
Sounds like a very strong optimization problem. Hopefully Prof could help us out with that.
Sorry.
No. I was going to ask any more questions.
On that, I guess, to Chris's point, I think that might be an interesting thing to probably, I mean, this is a bit of an aside, right? Because I know it's not really a PhD in optimization per se, or necessarily on theoretical foundations of ML. But I do know, I think it's Anil Jain's group at MSU. I know they were looking into work on trying to find a representative capacity of convolutional neural networks for facial recognition, I believe. And at least looking at this, like I wonder if there's an interesting line of research there in terms of if there's a way you can characterize theoretically, like if there exists like some sort of neural architecture that can get you within some percentage of MSE with the VMAF. Like kind of like a kind of universal approximation theorem kind of thing, but kind of just tied to this particular function. But I guess it's more like a theoretical foundation type work. But it's very interesting.
Yeah, it is very interesting. A nice discussion. We should probably have as well.
One follow-up question: from your experiments, the data from the loss function, does it look similar to like when you actually use differentiable functions in terms of the loss curve?
So the loss functions, if you increase the value of alpha, the loss function is pretty unstable. You use a small value of alpha, it more or less resembles the traditional in the traditional loss curve. And in previous work that this is that this perceptually optimized model was proposed for still images first with no temporal components. And yeah, they found the same thing, that the bigger alpha you get, the more unstable it is. Yeah.
How does this work with other codecs and stuff that you see temporal information in different ways?
Yeah, well, that we just use white Gaussian noise for right now, so no codecs as yet. The next step actually is to look at the using this in a deblocking scenario, because